The next activity for building the Boe-Bot is to build a start-reset indicator circuit and program. A brownout is when there is a low amount of voltage, such as when the circuit is reset or there is not enough battery power. We are going to build an audible sound coming out of the Boe-Bot if a brownout or a start or reset occurs. We're going to use something called a piezoelectric speaker. This is what it looks like, and you can also see it here. On the left is the diagram version of the piezo speaker. A piezoelectric element is something that has a crystal inside. You also use these in your lighters where you hear that click. So a piezoelectric element gets vibrated, and you can choose how fast that vibration occurs, also called a frequency. All you need for this is your Boe-Bot assembled as you had before, the piezo speaker, and some jumper wires. Jumper wires are located in your kit and are small wires that are blue, black, or other colors. This is the diagram of what we're going to build. We're going to put the piezoelectric speaker on P4 or pin number 4 on the positive end and on VSS for our negative end. Similar to what we did with the LED lights, we are going to connect the pin on the left to the breadboard, but this time instead of using a resistor, we're going to just use some wires. Then you're going to also have a wire going into VSS. The more challenging part about this is that you have to know which row, not necessarily which column, but which row you have put the two prongs on the backside of the piezoelectric speaker. You need to make sure it is quite a bit to the right and make sure your positive end is facing down. According to this diagram, the positive prong on the speaker is in the fourth row up. So 1, 2, 3, 4. And if you put it in straight, you'll notice that the next prong of the speaker is 3 more rows up. What I'm going to do is leave it a little bit at an angle and not quite pushed in all the way. And that way I can see where to put my wires. So remember, we're going to use pin 4 and then attach that to wherever the positive end is. Okay, so I'm going to take my wire, put it in pin 4. So 0, 1, 2, 3, 4. So put your wire in. And then attach this one to the same row as your positive end of your speaker. And then similarly, we're going to do the negative end of the speaker in the same row. And now attach that one to one of the VSS spots. Now, again, this is using the Board of Education Revision C. If you're using a homework board, that will be a little different. Okay, now it's time to start programming. Similar to what happened before, we're going to use a command. This is a new command called FREQ, which stands for frequency, and out for a sound going out. So frequency out, we're going to have the pin number, how long in milliseconds, and the frequency that we want to do. If we want to do another frequency by changing the pitch, we could do that. But let's just start with a simple one. In the program, we're going to have pin number 4, a duration of 2 seconds or 2000 milliseconds, and a frequency at 3000, or that's the same thing as 3 kilohertz tone. Our program is going to be called StartReset Indicator.bs2. So let's go ahead and get our Parallax IDE software going. So again, new file, save file, and change the name to StartReset Indicator.bs2. And let's check out the example program here because it's a little bit more complicated than just the one frequency out that it indicated. So here's what it wants you to do. It wants you to do a debug with CLS, meaning you're going to have a new line with the word beep. Then you're going to do the frequency for 2000 and 3000 numbers after that. Then the more unusual part is a do loop command with a debug CR for a new line waiting for reset. And it wants you to pause every half a second. So it's going to have waiting for reset flashing on the debug window over and over again until the hardware resets. Okay, so let's go ahead and do this. So debug CLS, and again we want beep to be shown. Now we can do our frequency out command, pin number 4 for 2000 milliseconds at 3000 hertz. Then we're going to do the do loop command, where we're going to have the debug window have something else. And again, this is a CR, and we want it to say waiting for reset. Pause this for half a second, and then loop it until it is reset. Now there's no end here because we want the message to keep going. Save your file, turn it on, download it, and you can hopefully hear the beep and see the beep in the message and continuously seeing reset each time. So if you push the reset button, it should restart all of the program and have a beep and waiting for reset. So I'm going to go ahead and turn this off so we don't keep seeing that message occur. Okay. So it wants you to add this program that you just did to a different program. A long time ago, we had hello once every second.bs2. Let's go ahead and open that. And it wants you to copy the frequency out command from the start reset indicator we just made into once hello every second.bs2 program above the do loop section. Okay, so before we do that, let's go ahead and copy our frequency out command here. And then let's go ahead and open hello once every second. It should be in your list on the left. And then right above the do loop command, it wanted you to put in the frequency. Okay, let's see what happens. Turn it on. That's the old program. So now we're going to download the new one. Okay, let's try that again. Okay, so it did one beep after hello and then continue the exclamation point every second. Okay, so now we're going to get into something new, which is testing speed control with the debug terminal. So in this case, we're going to be graphing the servo speed compared to the pulse width. And so there's a debug terminal's transmit window pane, which looks like this. Now we're also going to use a new command similar to debug, but this time it's called debug in command. So the places the messages are viewed is called the receive window pane because that's where it receives information from the basic stamp. The debug terminal also has a transmit window pane, which allows you to send information to your basic stamp while a program is running. You can use the debug in command to make the basic stamp receive what you type into the transmit window pane and store it in one or more variables. So the debug in command places the value you type in the transmit window pane into a variable. In the next example program, a word variable named pulse width will be used to store the values the debug in command receives. So pulse width is our variable, VAR for variable, and word for the large amount of numbers. Then we can do the debug in command to capture a decimal value that you enter into the debug terminal's transmit window pane and store it in pulse width. So we don't know what pulse width is, but the transmit window will then change pulse width into some sort of number. So while the program is running, we can then do pulls out 12, and whatever the pulse width is, we can then change the servo speed. Okay, so let's give this a try. So first we need to name our program test servo speed.bs2. So let's take a look at our directions because this is a little unusual. Continue this activity with the Boe-Bot sitting on its nose, which is the front side that's flat, not the one with the wheel. So let's go ahead and do that. Doesn't really stay too well, but that's okay. So enter, save, and run the test servo speed.bs2, and then point at the debug terminal's transmit window pane with your mouse and click it to activate the cursor in that window for typing. Type 650 and then press the enter key. Verify that the servo turns full speed clockwise for 6 seconds. So remember, 650 is one of our numbers we used earlier to make it turn clockwise. And then we could do it again for 850 to make it go counterclockwise. Okay. I'm going to now copy and paste the entire program from the example into the software. But let's take a look at what each one of these do. First, we have a counter variable as we had before for our for and next command. We have a pulse width, which is what we're going to input directly into the um, transmission window. And then the pulse width comp is another variable, which is going to be based on the pulse width that we put in. So first off, we have a frequency out, which is what we did before to indicate that the signal for the program is starting. And then a do loop command where you have a debug enter pulse width, and it's going to wait for whatever number we put in for the debug in DEC, some sort of number, and pulse width. Now pulse width comp is equal to 1500 minus the pulse width that we put in. So this is defining pulse width comp as one of the variables. Now for the for next, we're going to go counter equals 1 to 244, pulls out for pin 12, which is directly equal to the pulse width that we put in, and pulls out 13 is going to be pulse width comp, which is the 1500 minus whatever number we put in. And then the normal pause for 20 milliseconds next, and then loop it again. Okay, so let's see what happens. So we copy this, put it in. Remember to save your file, download it. Again, make sure your power's on. Okay, I'm going to go ahead and push reset here after turning it to number 2. Okay, so enter pulse width. Now, where do you enter the pulse width? In Windows, which is what the book is referring to, there should be a separate window that appears. In the Chrome app, it's not super obvious, but it's between this window on the top and this window on the bottom in this tiny little area where you can type something. So according to our directions, it wants you to type in 650 and then press the enter key. Okay, so let's see what happens when we type 650 and we push enter. And so it's looping again back to enter pulse width because it wants you to be able to do it again. So when it's done turning, this time we're going to do 850. Now, it wants you to check the RPM for the range between them, but that's not really necessary. Let's just keep going. So what you can do is you can try all of these pulses and see how far the wheel turns and see what it does. But again, that's not really necessary. It's just the different numbers indicate how far the wheel will go based on time and rotations per minute and things like that. Now remember, we need one wheel to be rotating clockwise and one wheel to be rotating counterclockwise. So the pulse width comp variable is 1500 minus whatever you put in. So if you put in 650, we need the other one to be 850. Each time they're going to add up to 1500. So let's say we wanted both of them to completely stay put. We would put 750 and 750, and that would be not moving. So if we put 650, we need 850 on the other wheel. So one way or the other, we need to indicate to the servos what their speed is based on the duration argument. Now remember, the closer you are to 750, the slower the wheels will turn. Now the 244 is to indicate 6 seconds based on how long it takes for this to complete. So hopefully you understood everything that was happening. All of these things we've already done before, but it can be just a little confusing starting to put everything together in one program. Okay, so then it wants you to start doing graphing pulse width versus rotational velocity. So let's take a look at the figure. So pulse width in milliseconds, remember that 1.5 is our 0 rotations. And then if you go less than 1.5, which is the 650 or anything lower than 750 from before, then now you have a rotational velocity going negative. And then if you go higher than that, you then have a positive. Now, if you decided to actually do this on your own and you calculated the RPMs at each one of these pulse widths, you would get a graph that looks something like this. And so the range of rotations per minute, RPM, is negative 48 to positive 48, which is only in reference to the clockwise being negative and counterclockwise being positive. So it's quite a bit of math to show what you want and where in terms of how fast you want the wheels to turn in rotations per minute. But this is just a nice graph to help you understand how to um, control the speed. So again, I want you to do this on your own and try this in a table and then plot the points on a graph, which I'm going to skip for now because that's a really lengthy project. But if you're up to it, go for it. Okay. Now, I don't know about you guys, but I want to see my Boe-Bot actually move in a certain amount of time at a certain speed. That's what I want to happen. So I'm going to go ahead and do that. I want to program this to actually go somewhere. So this program is already set for this to go for a certain amount of rotations or duration for 6 seconds. Now, I don't have a very big desk, so I'm going to make this go a little bit slow. So I want this to be really close to the 750 number. Okay, so let me go ahead and turn that to the 1. Oh, actually, I can just start the program. So I have my beep saying I can enter a pulse width. Let's do 740 and let's see if it goes. And it moved. Okay, let me do really close to 750. Let's do 749 and try it again. Okay, so that's too close. Let's try 745. Okay, so notice that one of the wheels didn't really turn too much because that wasn't enough voltage. So let's try 740. Okay, so for some reason mine is turning, which means that one of my servos is, or the wheels are sticky or something like that, but it should be rotating at the same speed. Let me go ahead and check that. Oh, it is. Okay, so the rubber band moved a little bit, which makes the wheel move unevenly. Okay, let's try this again. Okay, so at too close to 750, it appears there's not enough power going to both servos. But if you do the max RPM at 650 and then 850 with the subtraction, we end up having it going straight. Okay. All right. So hopefully you got a little bit out of the troubleshooting with this, that you weren't too worried about that. Turning and things like that. Remember, turning is where each of the servos are not moving at the same speed, but it can be just because you don't have enough power going to both of them because you're too close to the center and they're not exactly perfectly centered for the um, number of milliseconds we wanted it to be, the 1.5. But you've learned a new command. You've learned how to include a piezo speaker and the frequency out command. You also learned about the debug in command and where the transmit window pane is, which is not a window, but just a little area inside the Chrome version of the Parallax IDE software.